Now let's talk about errors of prediction. Okay, remember that error is just a difference between the real y value and the predicted y values. And the errors sometimes are called residuals because it's what is rest after you subtract the part of the variation of y that model predicts. You can find a very clear similarity with ANOVA. We also subtract systematic part and then we have the residuals. Here we also subtract systematic part, the part that model explains, and then we have the residuals, right? And you remember that if you subtract all systematic part, residuals should be random. They should be normally distributed and have average 0. That's what we discussed in ANOVA. And here it's absolutely the same. Residuals, if your regression model is good, residuals should be normal. They should not depend on y values. They should be normally distributed, and they should have a 0 average. Well, in fact, the way we make a model, residuals will always have 0 average, so we don't have to calculate average here, and we will not lose any degrees of freedom for this calculation. But we always have to check how random the residuals are and are they distributed normally or not. Let's see how we can do that. Well, that's the plot that you can check the randomness. Here I have the real y values, and here I have the residuals. So it means that it's E, where it's y minus yp. Okay. So, and the idea is, if residuals are random, they should not depend on y. They should be randomly scattered on this plot. And you can see it's not exactly like this, right? So you can see some small trends, so we can see some small patterns like this. Okay. So the residuals could be better. Okay. It's not very clear trend, but I think we still have some systematic variations that we do not take into account by using only H. We will discuss how to improve that in the next lecture. So far, we will just take it as is. Now let's check the normality. We know how to check normality. We need to use a cuckoo plot or Q-quantile normal probability plot, and apparently also Shapiro test. And again, even though the points align sort of around this, very close to the straight line, I can see some sort of systematic trends. Might be not very clear, but I still think that something is not captured in this data. So, of course, income depends on age, but we probably have some other variable that also influence the income. And simple linear regression simply does not allow us to capture this variance. Okay, but once again, we will leave what we have. That's the model what we have. Okay. Now we can calculate also an important characteristics of the distribution of errors. It's a standard deviation. Because average is 0, average of errors is always 0, we need to calculate standard deviation in order to see how big the spread of the errors is. Okay. That's the way we calculate it, and it looks a little bit weird because, in fact, you remember that standard deviation looks like this. It's you take error minus average error, square it, divided to n minus 1. And you remember why n minus 1, because we lose 1 degree of freedom when we calculate average, right? But now look. First of all, we don't need to calculate average. It's average error, not E, of course, not Y. We don't need to calculate average. We know that by default, that's the way we fit the model. The average error is 0. Okay, so that means that we can rewrite this formula as following. So it's sum of squared errors divided to n. We don't lose any degrees of freedom here, right? Or it will look like this. What is E? It's y minus yp, right? Squared divided to n. Now let's think why we have n minus 2 and not n. Well, to make a regression model, you need to compute two regression coefficients, B0 and B1. So you use the same values. Originally, you have independent values and independent values. Then you use the same values to compute two statistics, B1 and B2. Okay, and then you use these statistics to make predictions and to get errors. And then you calculate standard deviation for the errors. So standard deviation for the errors depends on these two statistics. Therefore, you lose 2 degrees of freedom when you calculate the regression coefficients. So there is nothing, even though it looks a little bit strange at the beginning, in fact, there is nothing wrong in this formula. So that's the way to calculate the standard deviation for your errors. Okay. Now, how it looks like when you have a big or small standard deviation. Well, apparently, if you have a small standard deviation for your errors, like in this case, the points align quite close to a straight line when you look at the predicted versus measured plot. Okay, but if a standard deviation for your error is a little bit larger, then it looks like this. So you can see that the points are more scattered, so the predictions is not very good in this case. Then if we calculate all the statistics for our case, we already know this, we already know the formula and the correlation coefficient. We can say that the residuals indeed look random and normally distributed, but from my point of view, of course, it's subjective opinion, but we will test this later. There is still some systematic variation in the residuals, okay? Then the coefficient of determination is 0.78. It means 78% of the income variation can be predicted by the variation of age. And then that's the standard error. So this is the standard deviation for errors. It's 4,227. You remember the standard errors are normally distributed. In this case, our sample size is relatively small, so we can use a t-distribution to assess uncertainty, right? So in this case, it means that y is yp plus minus t times standard error, right? For example, if you take two standard errors for 32, I think it will be approximately 95%. And it gives you almost 8.5 thousand, which is quite a big spread. So it's plus minus 8.5 thousand uncertainty. But this formula is not actually quite correct. You will find out in the next video that actually the error will be even larger because of the uncertainty in regression coefficients. So that's the way how to assess the quality of your model. And in the next video, we will discuss the inference. So how to find out the real uncertainty for the predicted values. Why we should take into account something else, but not only the standard error of prediction.